Hello, this is FlippedHarber for Precalculus. In this video we'll cover section 3.6, Complex Zeros, Quadratic Equations with a Negative Discriminant. Our objectives for this lesson are to add, subtract, multiply, and divide complex numbers, as well as solve quadratic equations with a negative discriminant. Our topics include imaginary and complex numbers, conjugates, and quadratic equations. Our outline for the video, we'll start by talking about imaginary and complex numbers, then look at the sum and difference of complex numbers, as well as the product of complex numbers. We'll talk about conjugates, we'll look at some theorems concerning conjugates, then we'll look at writing the reciprocal of a complex number in standard form, as well as writing the quotient of complex numbers in standard form. We'll look at some rules for the powers of I, and we'll look at writing the power of a complex number in standard form, and then end with solving a quadratic with a negative discriminant. Now, you should all be aware of what imaginary numbers are. An imaginary number is the square root of -1. Now, this is a complicated idea that we quite often leave till later when we talk about math. Well, now's later. So, you know that I equals the square root of -1, which means that I squared is equal to the real number, -1. Now, a lot of times we ignore imaginary solutions. And you know that you have to ignore them whenever you see things like find all real. Maybe that's find all real solutions, find all real zeros. You're ignoring the imaginary. Without that word real, or if they say find all real and imaginary, that means that you do have to go through the process or finish the process to find the imaginary numbers as well. Now, let's talk about some ways that you should write imaginary numbers. If I ask you what the square root of 4 is, it's just 2. If I ask you what the square root of -4 is, well, it's equal to 2i. Basically, we deal with that negative inside the square root by just writing the I. Square root of 8, well, that should reduce down to 2 times the square root of 2. So the square root of -8 equals 2 square root of 2i. Square root of 13 doesn't really reduce well, so we usually just leave it like that. But if you see the square root of -13, well, that's equal to square root of 13i. That negative under the square root is kind of hidden away, tucked away in that letter I. Alright, let's talk about complex numbers. A complex number is a number that has a real component as well as an imaginary. In standard form, it looks like this: a plus bi. A is what we call the real part, and it always comes first. And b is the imaginary part. It always comes second. Both of these, either of these, neither of these could be negative. 4 minus 5i, that's totally legal. -4 plus 5i, that's totally fine too. Now, two complex numbers are equal if and only if the real parts are equal and the imaginary parts are equal. So if we say that a plus bi equals c plus di, it means that a has to equal c and b has to equal d. Well, duh. Let's talk about taking the sum and difference of complex numbers. It's really a lot like combining like terms. I want to add a plus bi and c plus di. Well, I combine a and c. So a plus c, and I combine the b and the d because they're both the imaginary parts. So b plus di. Same thing goes on when I want to subtract. A plus bi minus c plus di means that I group together the a and the c, so it's a minus c plus b minus d. Now, the most common mistake that people make is forgetting that that negative goes to that imaginary part as well, so it's b minus d. When we want to take the product of complex numbers, well, this should look a lot like a product of two binomials to you, and that's really how we deal with it. We FOIL. So we get a times c plus adi plus bci, and then that last term, bi times di, becomes bdi squared. Now, that I squared, as you know, is equal to a -1. So that last number is actually a real number. So it's ac minus bd plus ad plus bci. Just FOIL. A conjugate is an idea in complex numbers where we just basically change the sign in front of the imaginary part of the number. So if z equals a plus bi is a complex number, then its conjugate, denoted by this z with a bar over top, and that's just read conjugate of z, is defined as a minus bi. Just change the sign on the imaginary part of the complex number. Okay, leave the real number or real part of the number alone. Trust me, it's useful in a little bit. Let's look at some theorems concerning conjugates. The product of a complex number and its conjugate is a non-negative real number. If we say that z is equal to a plus bi, then z times the conjugate of z is equal to a squared plus b squared. Now a squared is the real part of the number, and since it's squared, that's always positive. B is the coefficient that's in front of the I. We're not squaring bi, we're just squaring b. That's going to be a positive number as well. So a squared plus b squared, always positive. Whenever you multiply a complex number and its conjugate, you always get a positive number. Now, the conjugate of a real number is the real number. Okay, well, if it doesn't have an imaginary part, there's nothing to change the sign on. So the conjugate of 5 is 5. The conjugate of a complex number is the complex number. That means that if you take the conjugate and then take the conjugate again, you end up with your original complex number. So that's read the conjugate of z is equal to z. Alright, so the next couple ideas are not theorems, they still deal with conjugates. The conjugate of the sum of two complex numbers is equal to the sum of the conjugates, which means I can either add the two complex numbers, then take the conjugate, or I can take each conjugate separately and add them. The same thing works with a product. You can take the product of the complex numbers, then take the conjugate, or you can take the two conjugates separately and multiply. Now, let's take a look at where this is useful. If I want to write the reciprocal of a complex number in standard form, that is 1 over the complex number. That's not in standard form because standard form a plus bi is not in a fraction. Now a and b can be fractions, but they can't be inside a fraction. So the way I deal with this is I actually use the conjugate of the 3 plus 4i. I multiply the top and the bottom of this fraction by 3 minus 4i. Now, why do this? Well, whenever you take a complex number and multiply it by its conjugate, it becomes real. So doing this turns the number on the bottom of the fraction real. Yes, we have a new complex number in the top, but that's okay. This is a lot like the process of rationalizing the denominator. We would rather have the complex number in the top rather than in the bottom. So 3 plus 4i times 3 minus 4i, well, that's 9 plus 16. Square the 3 plus square the 4. Now we're not quite done because we should distribute that 25, because 9 plus 16 is 25, so that it's 3 25ths minus 4 25ths I. Now it's in standard form. Now let's take this one step farther. Instead of just talking about a reciprocal, let's actually talk about a quotient, a complex number divided by a complex number. Here's the short story. We can't divide by a complex number. So what we do instead is we make that bottom number a real number by multiplying by its conjugate. So I multiply the bottom by 5 plus 12i. That's only legal if I multiply the top by 5 plus 12i also. Now, the product on the bottom, that's easy. 5 squared is 25, plus 12 squared is 144. On the top, I got a little bit more work to do. I have to FOIL these two. Now, if I follow the pattern that we talked about earlier, I take a times c, which is 5, minus b times d, which is 48, plus a times d plus b times c. Again, this is all over 25 plus 144. So what I end up with is negative 43 plus 21i all over 169. Now, I forgot to type it in here, but your last step is to distribute that bottom, that 169, and create two fractions. So negative 43 over 169 plus 21 over 169i. Alright, let's talk about some powers of I. We'll start out with I to the first power. Well, that's just equal to I. No biggie there. I squared we know is equal to negative 1. Now if you combine the two, that is I squared times I, you get I cubed. Well, that's negative I because it's a negative 1 times I. I to the fourth is equal to I squared times I squared, which is equal to 1. Now the pattern repeats. I to the fifth, well, that's equal to I. I to the sixth is equal to negative 1. I to the seventh is equal to negative I. And finally, I to the eighth is equal to 1. And then this whole pattern repeats. I to the ninth, I to the 10th, I to the 11th, I to the 12th. And then I to the 13th, 14th, 15th, 16th. So this pattern just keeps on going on and on and on. You will see higher powers of I, and you're going to have to get it all the way down to I, negative 1, negative I, or 1. Okay, that's what it has to get down to. I don't want to see any powers higher than 1 on an I. Alright, so why is this useful? Well, let's take a look at this power of a complex number in standard form. We want to basically take 2 minus I to the fourth power. And you should look at this like it's a binomial to the fourth power, because that's exactly how we're going to treat it. Now I could FOIL that all out, and that would take 8 or 9 hours, I think. Or I can use row 4 from Pascal's triangle. Row 4 from Pascal's triangle is 1, 4, 6, 4, 1. You should know how to make Pascal's triangle on demand. And even if you start with row 0 and make the rows, make the rows, make the rows, this should be faster than trying to FOIL this all out. So these become coefficients that I use on 5 terms when I multiply out this binomial. So it's 1 times the first term to the fourth power, so my 2 to the fourth power, plus 4 times 2 cubed times negative I, because that negative goes with the I, plus 6 times both of those terms squared, plus 4 times 2, that is my first term to a power of 1, times negative I cubed, plus 1 negative I to the fourth power. Now, these negatives on these i's get the powers, and they behave just like powers on numbers. The square will get rid of the negative, the fourth power will get rid of the negative. So things start to reduce down. 2 to the fourth power is 16. 4 times 2 cubed is 32, so my second term is minus 32i, plus 24. Now that negative 1 came from the I squared. So I squared is equal to negative 1, so we introduce a new negative 1 to replace that I squared. I cubed is negative I. So the negative that's inside, that's getting cubed, that's preserved, it goes out front, and the I cubed introduces another negative. And then my last term, the negative is not preserved by the 4. I to the fourth is 1, so it's 1 times 1 ultimately. Combine like terms, I get negative 7 plus 40i. Excuse me, that's not plus 40i. Oh well, you can figure it out. Negative 32i plus 8 should be a negative 24i, not a plus 40i. Alright, so all of this has been culminating into solving a quadratic with a negative discriminant. You actually already know how to do this. Taking this quadratic and moving everything onto one side, basically I want to use the quadratic formula now. Negative b plus or minus the square root of b squared minus 4ac. Now normally we would have ignored this because that discriminant, that number under the square root, is a negative. We're not going to do that anymore. We're not going to ignore the imaginary numbers. So we have x equals 2 plus or minus the square root of negative 16 all over 10? Well, we know how to deal with that square root of negative 16 now. We change it to a 4i. So 2 plus or minus 4i all over 10. I should distribute that 10 to the 2 and the 4, and I reduce it. I get 1/5 plus or minus 2/5 I. Okay, so that's it. Time to try some of these on your own. I'll see you in class, and I'll see you online.